Welcome back to Algebra 1. We're thinking about solving quadratic functions. We're thinking of solving them multiple ways. And so far, what we've done is factor and then use the factors to solve. So how would we solve each of these? Remember, you're welcome to use shortcuts. Whenever you recognize that you have one variable here by itself, that variable is going to have to equal 0. And if I have a nice simple factor like this, I change the sign when I take it out. The solutions of problem 1 are 0 and 9. I can have a number factored out as well. That doesn't change the fact that t equals 0. So in this case, I have t equals 0. And when I set this guy equal to 0 by itself, move the 4, changes the sign, and 4 divided by 2 is 2. I'm okay with shortcuts. In this one, I have two nice numbers, 0 here and negative 10 here. And these guys are not simplified all the way. Moving this over, dividing by this, I'm going to get negative 2. This is going to change to positive, and when I simplify it, it will be positive 4. Hopefully that's what you would have gotten. So if we could find zeros of quadratics, we can find zeros of polynomials in some of the same ways. And then we'll also take a look at a couple real-world problems. So we need to solve by graphing. And in doing that, we need to start out by writing the equation in standard form. So I want that 3 to be moved over so that the equation equals 0. That's the way I want to take it. When I don't have the graph, I need to make the graph. Right now, we're going to use a t-table. So we plug in some numbers. Plugging in 0, we end up getting, when we calculate that, negative 3. Plugging in 1, we end up getting 0. Plugging in 2, we end up getting 5. And what we notice are these numbers are farther apart than these numbers. So I'm not going to go to 3, I'm going to go to negative 1, negative 2. 5 numbers is usually a pretty good starting point to figure out what the curve of the graph looks like. 1 minus 5 is negative 4. And there we end up getting 4 minus 3. So what I might notice as I'm starting to go back up, it might be a good idea to plug in negative 3. 9 minus 6 minus 3 is 0. So we actually found our two zeros here. We're going to graph those points. At 0, we were at negative 3, negative 1, so making our attempt. Doesn't work well while writing backwards. So we make a attempt at graphing, and what we notice is we did get good points here, so we know that the solutions are going to be at 1 and negative 3. So that's what we did yesterday. And if we take a look at these, we always want to try to put them in standard form, which means I know I'm going to add 16 to both sides. And I get x squared minus 8x plus 16. I do always try to figure out, can I factor it? And I notice that 16 is going to be negative 4 times negative 4, and that would work. Because if I can factor it, that's a real nice way of solving. Remember, the factors change sign when I solve. And there are two 4s here. I'm just going to write one of them. We won't really need to know that there's a second one until Algebra 2. If we know that we have this point, think about where that is on the graph. That point, that solution, is at 0, 4, right here. And there's no other solution. There's no other place that it crosses the graph. We actually have a very standard shape of these graphs. It's symmetrical. So I didn't make a t-table on this, guys. Sorry, chicken scratchy. But I can solve it. That solving gives me points on the x-axis, and that might help me know where my general shape of my graph is. Putting in standard form, now I'm going to choose to move this guy because I don't like negatives in front of the x squared. Doesn't matter if the 0 is in front or at the end. Oh, that's a little neater than normal. Okay, so once I have that, can I factor? Are there factors of 4 that add to give me 2? And there actually aren't. So now what do I need to do? Make a t-table. And off to the side of this, I'm going to substitute these in. I'm probably going to notice when I solve these that I'm going to blow up my equation fairly quickly. This ends up being 2 squared 4, 4, 4, 12. So these are getting larger, and I haven't come close to finding a 0 yet. So I'm going to end up going back the other way. So when I try the next 3 sets of numbers here, and I plug these in, I end up getting 3, and 4, and 7. I never crossed the zeros. All of my numbers are positive, and if I go to -4 or if I go to 3, I'm going to get my numbers blowing up on me. So what does this look like on the graph? Turns out my graph looks like this. Where are my solutions? I never actually crossed the x-axis. And so for this type of problem, I need to recognize that there are no real solutions. It's perfectly possible that my graph never crosses, and when that happens, no solutions. So now I have polynomials that have a degree larger than 2. They can be graphed. If I can see the graph, I can see the solutions. The solutions are always where I cross the x-axis. So I can actually write out the solutions on these. X equals, first point here is -4. Next point here is -1. And the last point is +2. So I have solutions. I could also write factors. So every single one of my solutions gets written as a factor. Remember, I change the sign every time I go from factors to solutions. And I can say that equals 0, and that's my factors. Solutions here. Notice here I have a 1, so that's going to be at x equals +1. Here's a solution at 2, and there's a solution at 3. What I notice when I write the factors is there is a difference between this and this. I cross the graph here, terms off of it here. So when I go to writing factors, and I don't quite believe you're going to be writing these all out today, but this is an FYI. Each solution gets written as a factor. When the graph does funky things around that point, that factor may be more than once. Main thing you're going to be looking for is what are the solutions. The next thing I have is some real-world type problems. You're going to have a couple problems where they say find out the value of the function like every couple of seconds, and what you're going to do there is make a t-table. So we have a football player kicking a football from 2 feet above the ground. We have an initial velocity, and this equation we will see over and over. You'll see it mostly when you get into physics. This deals with the effect of gravity on anything that's moving. So once you drop something, kick something, throw something, the equation, this deals with gravity, the -16. This is the initial velocity, and this is my initial height. So find the height of the football after each second that it's kicked. So we're going to make a t-table. And that t-table starts at 0. You're just going to number crunch. And what I notice is my numbers start going up. This was my high point, but both of these are pretty high. And then it starts coming back down. And we do get to the point where it can't go below ground. So we definitely stop here because my football can't dig into the ground. The next part of this is we want to estimate when would the football be at 50 feet. Well, here we're at 61. Here we were at 2. So we know that somewhere between these two, we're going to be at 50 feet. So I might make a guess. I mean, this is closer. So I might make a guess that it's at 0.75 seconds, 3/4 of a second. And I also notice I'm here just before 4, pretty close. So maybe this is at 3.9. Those are guesses from the table. When does the ball reach 50 feet? It reaches it twice, on the way up and on the way down. But we can also take a look at a graph to help us find those things as well. Excuse me, we have these two estimates at 0.75 and 3.9 seconds. That's one of the ways. There are two different ways that we could graph. The first way that we're going to graph is we're going to move everything over to one side, say it's equal to 0, and then the zeros, once I have that graph, are at these 2 points. Do they look like they're approximately 0.75 and 3.9? The second way that I can graph is I can graph the two separate sides of the equation. So I'm going to graph my first equation as it was, and then I'm going to graph a line at 50. So now, where my solutions are these two places. Do they also look like x is 3/4 and x is 3.9? All three of these ways work to find solutions. Jennifer hits a golf ball. It starts at ground 0, and we have an equation that looks very similar. Find the height every 1 second, that's our make a t-table, and then find the highest point that our golf ball reaches, and also when it hits the ground. So I'm thinking it might take about 5 seconds, and I'm going to do all the number crunching that goes with that. So we've done the calculations. It is plug in number crunch. Notice I stopped at 7 because that was when it went into the negative numbers. And we have our regular graph here. And we notice that our high point in our table was at 3. When we actually graph and try to make it an even curve, it looks like it's a little bit higher than that. So high point, and we're estimating from our graph, it looks like it's at 158, 157, 158, either of those would be good. Where does it hit the ground? Hits the ground right here. At time, here's 6 seconds, here's 7 seconds. Hits the ground at, looks like 6 1/4. So once we have that graph, we can start answering different types of questions. When will the height be this? Well, it's going to be at 2 points. What's the high point? High point can be a type of solution. When does it hit the ground? So all of those are different types of questions that you're going to have asked. You will have a couple word problems that you're doing that are very similar to these. Your homework is on Google Classroom. If you have any questions, please shoot me an email, and have a good day.